In this lecture, we are going to discuss about the solution of a linear programming problem, right? And we solve this linear programming problem by graphical method. And the linear programming problem, it is given that maximize z, this is equal to 6x1 plus 10x2, subject to 3x1 plus 5x2 less equal to 10 and 5x1 plus 3x2 less equal to 15 and x1 x2 greater equal to 0. And we know that this relation, that is z equal to 6x1 plus 10x2, this is known as objective function. Right? And these two conditions, that is the subject to two conditions, these are known as constraints, right? And this is also a constraint, or it is also said to be non-negative restriction. Okay, now we first draw the graph of this LPP. We first draw the constant or the equation of constant in a graph with satisfying non-negative restriction. Okay, now we draw here x1 axis and x2 axis. We draw the first quadrant because if we satisfy the non-negative restriction, then our aim only on the first quadrant, because in the first quadrant x1 and x2 both are greater equal to 0. Now to draw the first constant, that is 3x1 plus 5x2, this is equal to 10. Okay, and to draw this we write it as an intercept form, that is x1 by 10 by 3 plus x2 by 2, this is equal to 1. So clearly this line cut x1 axis at here, this is 10 by 3 comma 0, and cut x2 axis at 0 comma 2, and we join this by a straight line. This is the first constant, and we write here this is 3x1 plus 5x2, this is equal to 10, and it is given that this is less equal to 10. Now we draw, or now we find the region in which direction. We put any point of this two-dimensional plane in this relation, okay, which is not on the straight line. Let it be 0 0 0 0, not on the straight line, because this straight line not passes through the 0 0. Then we get that 0 plus 0, because 3 into 0 plus 5 into 0, this is equal to 0, and it is obviously less equal to 0. So 0 0 satisfy this condition. So we say that towards the 0 0, the origin of, towards the 0 0, the region of this line occur. Okay, so we indicate here by an arrow towards the origin. Now we draw the second line. This is given by 5x1 plus 3x2, this is equal to 15, and given by x1 by 3 plus x2 by 5, this is equal to 1. So we get, this is, because of this 3 equal to 3 comma 0, and this is 10 by 3, that is greater than 3, so let it be at the point 3 0. Okay, and 0 comma 5, so it is here, this is 0 5. Okay, and we draw the straight line, and we write here this is 5x1 plus 3 x2, this is equal to 50. Now to derive the position of region satisfying by this condition, here also this is less equal to 50, and since it is also not passes to the origin, and we put 0 0 in this relation, so we get 0 plus 0 less equal to 15, so it also satisfies this condition. So the region is also towards the origin. Okay, and we know that x1 greater equal to 0, that is x1 greater equal to 0, this because this is the line, here x1 equal to 0, that is x2 axis. So x1 greater equal to 0 means this position, and x2 greater equal to 0, so this is this region. So we said the region satisfying the constraints together with the non-negative restriction, it is clear that this is the region. We said the region. Okay. Now we say that this is the point O, let it be A, let it be P, and let it be B. Okay, and we say that the region shaded region O, A, P, B is physical region. Since it satisfies all constraints and non-negative restriction. Okay, so we get the feasible region. This is the feasible region shaded, and this is the feasible region OAPB. Now to find the vertex P, we solve both the equation. This is 3x plus 5y equal to 10 and 5x plus 3x2, this is equal to 15, and getting the result as 45 by 16 comma 5 by 16, we solve and get this point. Okay, now since the feasible region is bounded and bounded by the four vertices O, A, P and P, so now this problem we solve into two methods. Okay, and the first method is taking only the boundary point, taking only the vertex point, and in second method we solve this by taking or by drawing dotted line. Okay, and we discuss these two methods one by one for this problem. We first discuss by taking the four vertices. Okay, now since here we write, since feasible region is bounded, so we get, here we make a table, and in the first column of the table we write vertex. Okay, in the second column we write here x. In the third column we write here, this is x1, this is x2, and in the fourth column we write here z. What is z? Z is the value of objective function. This is 6 x1 plus 10 x2, and now putting one by one of the vertex. Here four vertices are O, and at O this is 0 and this is also 0 because the coordinate of origin is 0 0. And putting the value of x1 and x2 here, we get z equal to 0. Okay, and then we put A, vertex A, this means 3 0. Then clearly we get this is 18, right? Now put P, this is 45 by 16 and 5 by 16 and get 6 into 45 by 16 plus 10 into 5 by 16. Getting the result, this is 20, and also for the last vertex, this is B. B is x is 0 and y is here 2 because this is 0, 2, and give the result is z 0 plus 20, this is equal to 20. Okay, now we write here 20. Now the problem is maximization type. Okay, it is given that this is maximization problem, and we get the maximum value of z at two vertices, at P and also at B. So from this two condition, we say that the problem has infinitely many solutions. Why we say in this type of comment? Because if the maximum value of the objective function occurs more than one vertex, here occurs at P and occurs at B, so we say that the maximum value or the optimal value of the objective function occurs at all points on this line segment, and the number of points on this line segment is infinite. So we say that there be infinitely many solutions, right? But maximum value of z is equal to 20, right? So here we write, so maximum z, this is equal to 20, and it occur at the vertex P and B both. Okay, so we say that all the points on the line segment BP, okay, line segment BP gives the max z. Okay, hence problem has infinite solution with z max, this is equal to 20. Okay, we get the answer. In second method, that is the method of drawing dotted line, we first choose a particular value of z of the objective function, right? We have to choose a particular value of z of the objective function, and getting this as a straight line, and we draw this straight line by and dotted line. Okay, and here the restriction to choosing the value of z, we choose the value of z in such way that this straight line be in, or we say must be in, the feasible region, right? We first let a particular value of z is equal to 10. Okay, and then objective function becomes objective function becomes 6x1 plus 10x2, this is equal to z, and this is given by 3x1 plus 5x2, this is equal to 5. And it is clear that this objective function is parallel to the first given constant. Okay, here also with 3x1 plus 5x2 less equal to 10. So this line must be as looks like this. Now we get two cases here. In this case, the problem is of maximizing type, and in another problem, maybe this is minimizing type. Okay, there are two processes to get the maximizing value of z or to get minimizing value of z. Okay, since the problem is maximizing, so we move the dotted line parallel to itself away from the origin, because of this is maximizing problem. And if this problem is minimizing type, then we move the dotted line parallel to itself in both case and towards the origin. And in both case, we move the dotted line until it contains only one point of the feasible region. Okay, but in this case, if we move this line or this dotted line parallel to itself away from the origin, that is in this way, we see that when we take z equal to 20, okay, z equal to 20, then this function becomes 6x1 plus 10x2, this is equal to 20, that is 3x1 plus 5x2, this is equal to 10. This is nothing but the first constant, first given constant. So we say that at the last position, when we move it parallel to itself away from the origin, at the last position, this dotted line coincides with this constant, and if we move this further, then the dotted line is outside the feasible region. Okay, and since it is coincide with these constraints, okay, at the last position, so we say that the problem has infinitely many solutions. Okay, that is, here we write, since at the final position, when z equal to 20, then dotted line coincide with the line PB. Okay, and after that, the dotted line, after that, this line is outside the feasible region. Okay, so we say that problem has infinitely many solutions, with maximum value of z, max z, this is equal to 20, because at the last position we take z equal to 20. This gives the maximum value of the objective function, and this is the complete solution of the problem. We solve this problem by two methods. Okay, this is very interesting and important problem of linear programming problem, and this is solved by graphical method. Right? Thank you for watching.